Okay, so in this video we're going to be moving on to finish up the unit, and we're going to be doing basic calculations with the Bohr model of the atom. Before we get to that, just a little review question. This would normally be a warm-up question, but I want you to take a look at this question and read what it has to say and see if you can answer this question. And on the next slide, I'll put the answer that I came up with. Again, when you're doing an explanation question, make sure that you address each part of the explanation question. Make sure you write in complete, coherent sentences. So for example, this question says, in terms of electron energy levels. So that means your answer somewhere has to reference electron energy levels. And we basically want to explain why are there lines missing from the absorption spectrum of hydrogen. Okay, so see if you can answer this question, and then compare your answer to what's on the next slide. Okay, so here is a possible answer to this question, at least one that I came up with. I said that white light contains photons of all different energies. As these photons pass through the gas, some of them are absorbed by electrons in the gas atoms, causing the electrons to become excited and go up to higher energy levels. Because these photons were absorbed within the gas, they are no longer present on the other side of the gas and therefore are represented by missing lines in the absorption spectrum. So I did reference electron energy levels, and I did answer the question as far as explaining why there are missing lines in the absorption spectrum. So that is not the only way you can answer this question, maybe not even the best way to answer this question, but it does address the question that's being asked. So remember, when you're doing an explanation question, always make sure that you answer the question fully and answer the question that's being asked. Okay, so in the last video, we did some calculations with photon energy. So just to recap, before that we were talking about the Bohr model of the atom. And in the Bohr model of the atom, you have different electron energy levels. And in order for an incoming photon to promote or excite an electron to a higher energy level, it has to have what I said was the correct amount of energy. Now, if you go back and look at Bohr's postulates, you'll see that basically what that means by correct amount of energy is that the photon has to have an energy equal to the difference between the two energy levels. And when I say difference here, I mean the mathematical difference. And so now we're going to see energy levels that actually have numbers attached to them. Also remember that when an electron becomes excited, in other words, when it goes to an energy level above the ground state, it naturally wants to fall back down to a lower energy level, and when it does so, it loses energy, obviously, because it ends up at a lower energy level, and that energy has to come out somewhere, and so it comes out in the form of a photon that the electron emits, which has an energy equal to the difference between those two energy levels. Okay, so again, what we're looking at here is the difference between two given energy levels. Okay, so here are some different energy levels. Normally this would all be shown on one picture, but they're shown here separately just so you can distinguish between the ground state. Remember, ground state is n equals 1. That's the lowest possible energy that an electron in that atom can have. And then we have these higher energy levels. Don't forget that n equals infinity corresponds to ionization. Now, notice the values here kind of numbered a little strangely, and we're not going to get into why exactly, but they're numbered to have negative energy values, with n equals infinity corresponding to 0 electron volts. Okay, so it's a little backwards from what you might think, because you might think, oh, higher energy levels, the number should be higher, and they are technically, because they're becoming less and less negative, ending at 0 at n equals infinity. So we're not going to get into, why is it, numbered with negative values instead of numbered at 0 in the ground state going up from there, because that's not that important. Okay, but do you notice we have some values here? Now these are the electron energy levels for hydrogen. The numbers would look different for different atoms. Okay, but this is what they look like for hydrogen. Okay, so notice when we have actual values here, when we talk about the difference between two energy levels, we're talking about subtracting these two values. Okay, ignoring the negative signs, because all we really care about is the absolute value of the difference between two energy levels. So for example, the difference between n equals 1 and n equals 2 for hydrogen, we can see right away, just looking at the absolute value, would be 13.6 minus 3.4, which of course would be 0, or not 0, would be 10.2 electron volts. Now do pay attention to the units. Remember that when you're doing a calculation with like frequency or wavelength, the energy has to be in joules. Okay, but it's common to be given these pictures in electron volts. Do pay attention to those units. Okay, so when we talk about the difference between two energy levels, that's what we're talking about. Okay, so what we're going to do now is we're just going to go through some basic calculations with the Bohr model of the atom. So example 4 says, look at the energy level diagram to the right. In order to knock an electron from the ground state to n equals 2, how much energy must an incoming photon possess? Now again, if the electron is sitting down here in the ground state, in order for this photon to come in and excite it and knock it up, it has to have an energy equal to the difference between these two energy levels. Now luckily for us, we just calculated the difference between n equals 2 and n equals 1 for hydrogen. That's 13.6 minus 3.4, which is 10.2 electron volts. Okay, so that's the answer to the first question. The incoming photon has to have 10.2 electron volts in order to be absorbed by that electron. Now, what if it has, let's say, I don't know, 9.8 or 10 or 12 electron volts? Then the photon just doesn't get absorbed at all, it just passes straight through the electron. Remember, the only photons that get absorbed are the special ones that have an energy just equal to the difference between two different energy levels. And so if you're shooting photons with all different energies at this electron sitting in the ground state, the vast majority are going to just pass straight through the electron. They're not going to get absorbed. The only ones that do get absorbed are the ones with that precise difference between two successive energy levels. Okay. So, the next question says an electron falls from n equals 3 to a lower transition via two possible transitions. What energies will the released photons have? Okay, so I'm going to erase this a little bit here, just so I have room. Okay, so if I have an electron that's become excited somehow, and it's sitting in n equals 3, it's going to fall down naturally, because everything has a natural tendency to go to a lower energy level. Now, the only two possibilities are that it goes from n equals 3 to n equals 2, or from n equals 3 to n equals 1. Now, there's no way to predict which one is going to happen. It's kind of a random type of thing. Okay, but those are the two possibilities. Now, at least those are the two possibilities coming directly from n equals 3. Of course, if it goes from 3 to 2, it can also go later on from 2 to 1. Okay, but this question, we can tell from context, it's only talking about directly from n equals 3. What energies will the released photons have? Okay, so the electron going from 3 to 2 is going to emit a photon with an energy that has the with an energy of the difference between those two energy levels. So from 3 to 2, the energy of that photon is going to be, let's do this calculation. And again, notice I'm ignoring the negative signs here just because I really only care about the magnitude of this answer. I don't really care about the signs. Negative signs don't really matter. You can't have a negative energy for a photon. That doesn't make any sense. Okay, so when the electron goes from 3 to 2, the photon that comes out has an energy equal to 1.89 electron volts, because that's the difference between those two energy levels. Now, when it goes from 3 to 1, the photon that comes out is going to have an energy equal to 13.6 minus 1.51, which is equal to, I'm just going to type this into my calculator, 12.09 electron volts. Again, pay attention to the units, because if you have to take this energy and then do a calculation with it to find a wavelength or something, you do need to convert the energy to joules, because those equations only work if the energy is in joules. Okay, so these two are the answers for this question right here. And then the last question says, how much energy does it take to ionize this atom? Now remember, to ionize an atom means to remove an electron from it. In other words, if we have an electron sitting in the ground state, its happy place, to ionize it corresponds to moving it from n equals 1 all the way up to n equals infinity. Okay. Now at n equals infinity, we say the electron has no energy because, well, it's no longer attached to the atom, so it's just out there on its own. And so the difference between those two energy levels would be 13.6 minus 0, which is 13.6 electron volts. In other words, hydrogen only takes 13.6 electron volts to become ionized. Okay, so that is the last question for example 4. Please pause it there if you need to, or if you need to write down any questions you have about that. We're going to do a few more examples. Okay, so take a look at example 5. Example 5 says a water molecule requires about 33 electron volts of energy to ionize. Calculate the energy of a 33 electron volt photon in joules. Now remember, electron volt is a unit of energy. It's a unit of energy that we use because the joule is such a big unit of energy. It's not very convenient to use joules when you're talking about these small energy values. The conversion factor is 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Okay, so this first question is nothing other than a simple unit conversion. Okay, so if you type that into the calculator, you should get 5.28 times 10 to the negative 18 joules. Okay. The second question says calculate the energy of a microwave photon, which has a wavelength of 12 centimeters. Okay, so we're finding the photon energy. We're given a wavelength, so we have to use the equation that has wavelength. Do keep in mind that this needs to be converted because everything has to be in SI units. Wavelength should be measured in meters because meter is the SI unit for length. So this is going to be 0.12 meters. Okay, so we have Planck's constant h. I'm just going to plug that in. We have c. Remember, that's the speed of light in a vacuum. That's about 3 times 10 to the 8 meters per second, divided by the wavelength, which is 0.12 meters. And I'm going to type that in to my calculator really quickly. Okay, always make sure you pay attention to units when you do these problems. And I get 1.66 times 10 to the negative 24 joules. What conclusion can you draw from these two answers? Well, it takes this much energy to ionize a water molecule. This is how much energy a microwave photon would have. If you look at these and you look at the difference between them, the order of magnitude difference, this one is about 6 orders of magnitude, which is about 1,000,000 times smaller than this one. So in other words, microwaves cannot ionize water molecules because they don't have enough energy. Not only do they have enough energy, they're not even close to having enough energy to ionize water molecules. Okay, so this is something everybody hears as a child, and it's just not true. Microwaves cannot give you cancer. Okay, they just don't have the energy required to cause ionization, not even a little bit. Now, of course, I realize humans are not made completely of water, but look at the difference in the order of magnitude. There's like literally 1,000,000 times difference between the energy of a microwave photon and the energy required to ionize a water molecule. Okay, so that's again not even close. So microwaves cannot give you cancer. They are non-ionizing radiation. And now we've seen that for the first time. Everybody always hears as a child, don't stand too close to the microwave because you'll get cancer or something. Not true. Okay, it's just not physically possible. Now, that's not to say microwaves are safe because they can, of course, be dangerous to you. Microwaves could actually cook you if you got exposed to a strong dose of them. So I'm not saying microwaves cannot harm you at all. I'm just saying that they can't give you cancer because they're non-ionizing radiation. Okay, so pause it there if you need to take a look at that calculation. Okay, so a couple more examples. This one is showing us a electron transition from n equals 3 to n equals 1, and it says what is the wavelength emitted. Okay, now we did this problem a few minutes ago, and so I'm just going to put the work up on the screen and let you check it on your own. But of course, the energy of this photon is going to be equal to the difference between these two energy levels. We did that calculation a few minutes ago. So we would want to start by finding that energy, and if we want wavelength, that means we're going to use this equation that has wavelength in it, and that means the energy has to be in joules. Okay, so that's going to require a unit conversion. So here is what the answer would be. Actually pause it here and see if you can do this calculation on your own. And here is what the actual answer would be. 1.03 times 10 to the negative 7 meters. Now, just for purely reference points, it's very common to convert to nanometers in this type of situation, just because 400 to 700 nanometers is what humans can see. There's nothing at all special about nanometers. The only reason you would ever convert to nanometers is for comparison sakes. If you want to know, like, where does this fall in the EM spectrum? Well, it's below, it's shorter than like blue or violet light, so it's probably ultraviolet. Okay, but the answer to this question is this right here, 1.03 times 10 to the negative 7 meters. If it doesn't tell you the unit for wavelength, you should assume it's meters, because meters is the standard unit for wavelength. Okay, so again, this conversion to nanometers is done only for like reference sake. There's nothing special about nanometers. So hopefully you got that answer. And just a few more quick examples. Example 6, look at the energy level diagram to the right. What is the energy of the photon released in transition A? Okay, so here we're given some transitions, and they're labeled. Now, there's a problem with this picture. It's done incorrectly. For some reason, notice that the ground state is 0 eV, and then it goes up from there. That's not really how it should be drawn. I think whoever made this picture probably made a mistake there, but it's not that big of a deal. So the energy of the photon released in transition A, so here's transition A. Notice it is a downward transition, which does correspond to a photon being emitted, as opposed to an upward transition, which would correspond to a photon being absorbed by the electron. So what do we care about for this energy? We care about the difference between those two energy levels. And in this case, the difference would be 12.1 minus 0, which would just be 12.1 electron volts. Here you go. Second question says, state the energy of the photon involved in transition B and C and explain the difference between these transitions. If you look at B and C, notice that they involve the same two energy levels, but one is going up and one is going down. If you're ever asked to draw an arrow on one of these diagrams, please make sure that you label the direction correctly. Upward transition corresponds to an electron being absorbed. Downward transition corresponds to photon, let me repeat that. An upward transition corresponds to a photon being absorbed by the electron. A downward transition corresponds to a photon being emitted or given off by the electron. Okay, so the energy would be the same. That would be 10.2 eV minus 0, which would just be 10.2 eV. But one transition involves a photon being emitted, and one involves a photon being absorbed. So there you go. And by the way, transition D, in case you're wondering, is not possible. You cannot go from 0 in between two energy levels, because remember, in the Bohr model of the atom, the electron is not allowed to exist between two energy levels. It's not physically possible. Okay, the electron in the Bohr model can only exist in those certain allowed energy states. So transition D, just in case you were curious about that, that's not a possible transition. If this photon came in and hit an electron in the ground state with this much energy, it would just pass right through the electron and get ignored completely. Okay, so transition D is not possible. Okay, and one more example, I think. I'm going to erase that. Let's see. I think we've already done problems like this, we talked about the lowest state being ground state, n equals 1. Question, what needs to occur for an electron to be promoted from ground state to the fourth energy level? Of course, it has to absorb a photon with a certain amount of energy. Really, I want you to look at the second question. It says, how many possible transitions are there for this electron? What is different about each transition? So if we have an electron sitting in n equals 4, that's the fourth energy level, and we want to know how many different transitions are possible, what we do is we just write them out. And remember, if you have an excited electron sitting at n equals 4, it's only going to fall down on its own. Okay, so we want to write out the possible downward transitions. It could go from 4 to 3, from 4 to 2, or from 4 to 1. From 3, it could go from 3 to 2, or 3 to 1. From n equals 2, if it were to fall from 4 to 2, it could then go from 2 to 1. Okay, so that is 6 possible transitions, and each of those downward transitions would correspond to a different line on the emission spectrum. Okay, we can see that right here. This type of question about how many possible transitions are there is very commonly asked as a multiple choice question on the IB exam. Okay, so it all depends on how many energy levels you're starting with. If you have 4 energy levels to work with, that's 6 possible transitions. Okay, so I'm just going to really skip through these slides really carefully because I don't want this video to be too long. I do want you to look at this question and then the answer to the question. Okay, do make sure if you're ever given a wavelength in nanometers that you convert it appropriately. And if you're ever asked to draw an energy transition, make sure that you draw the direction carefully. Okay. Electron transitions leading to emission lines are always going to be downward transitions, because only when the electron goes down to a lower energy level do you get a photon being emitted. Okay. Emitted emission spectrum. Right, so there you go. So we are basically done with everything in this unit. The next assignment, you're going to have basically 3 Bohr model worksheets to work on just to get lots of practice. Please pay attention to the units. Please ask me if you have any questions while you're working on these assignments. Hopefully we did enough practice problems so that you kind of get the idea and the concept of what we're doing here. These calculations are much easier to do as long as you understand the concepts involved. Okay, so go back, make sure you took really good notes, make sure you're asking questions if you have any questions, and definitely ask questions. Please send the questions to me by email. Definitely ask questions before you submit your final assignment. Okay, so as always, it's been a pleasure to teach you this unit. I think we're about out of time for the school year, so this might be the last video, but I don't know, we'll see. Enjoy.